For today's quiz, we've got a very large Van de Graaff generator. We have two discharge domes, and they're equally spaced. This is a smaller, this is the larger. Each one goes to a metal pole that goes to ground. Our question for today is, if we were to turn on the Van de Graaff generator, to which of these two would it arc? Here's what your quiz looks like. As always, mark your answer as completely as possible and list your confidence. We have three typical student responses. It's either going to go to the small, the large, but to be honest, most of them don't offer any rationale for that. Most will simply say, if they're equal distance, and they are, and I'll show you, I'll just use a big insulator to show you. They're nearly identical in terms of their distance. They'll say, well, if the distance is the same, there's an equal likelihood of discharging to either side. So those are the typical responses that we get. All right, let's actually turn this on and then we'll provide an explanation. So if I turn the Van de Graaff on, it arcs to the smaller one. Why is that? Well, let's go do some theoretical work and try to explain this. All right, let's do a little thought experiment. Let's say we have a larger dome and a smaller dome, and I'll draw them. These are our discharge domes, or they could be Van de Graaff domes. It doesn't really matter. The key is, let's go ahead and connect these with a wire. This is a thought experiment that we can use to figure out about discharge. If I charge one or both of these up, they're going to have the same voltage. So let's start with that. I could say the voltage on this side must equal the voltage on this side. Clearly, there's going to be a difference in size. And when we mean size, we're really talking about the radius. So this side, let's use a capital R, big R. And the other side, let's use a smaller r, like that. That way we can keep track of what's going to be the density of electrons on each of these. We can then end up using our velocity formula, where velocity equals our electric field times our distance. Classic formula that we can use. So I'll end up saying, well, the electric field times the distance must equal the electric field times the distance. But because we're using radii, we should end up switching R and D. So let's go, the electric field on this small radius must equal the electric field on the large radius. From there, we can end up saying, we know the electric field is equal to KQ all over R, and that would be squared. Because we end up having different size charges, I can end up saying, well, let's use a capital Q here and a lowercase q on this side. So I can end up saying my electric field here is KQ all over R squared times R must equal my K capital Q, and I'll use my large R all over my R squared here. I think we can see right away that one of our R's would cross out on both sides. Again, small ball, we're going to use small q, small r. From here, we've got our KQ all over our R must equal our K capital Q all over our big R. But what we really want to know is the charge density. In charge density, we can end up saying where sigma equals the charge per area. Just like you might have mass density of mass per volume, we're going to end up talking about our surface area density. We really want area because that's where the charges are going to rely. So I can end up saying Q is therefore equal to sigma A. Now, we should probably use different sigmas for the big and the small ball. So I'll end up using, on this side here, I'll have K. Instead of small sigma, I'll use a capital sigma, sigma A, and then I still have my Q. We're getting rid of Q because Q is going to end up replacing that all over our capital R. On this side, I could have K would be our small sigma area, all divided by our little r. Again, sigma A equals our Q here, so I have my sigma A, and I can just use the capital sigma. I can also talk about area, where area in this case is going to be 4 pi r squared. In other words, the surface area of each dome is simply going to be 4 pi times their radius. On this side, it would be K sigma. Our area would be 4 pi r squared all over our r must equal our K capital sigma, and then our area is going to be 4 pi capital R squared all over our large R. Here I can end up canceling out one of these R's. I can also get rid of my constant, my 4, my pi, my 4, my pi. K is a constant. Get rid of both of those. Now I can end up saying I've got sigma R equals capital sigma capital R. Let's just do a little math here, and let's assume this radius is, we'll just say 3 times bigger, just to make our life easier. So I could say if capital R equals 3 times a small r, I can plug that in here. I can end up saying sigma R equals capital sigma, and this would be 3r. Notice the r's cross out. Sigma equals 3 capital sigma. In other words, the charge density on the smaller curvature is 3 times what the charge density is on the larger side. So we can end up summarizing and saying, as our radius decreases, our sigma increases. And I can draw that quickly. I can say, if I had charges that were lined up on each of these metal domes, I would have fewer over here and many more on the pointier side. So let's go back and show you what we can do with this information. Now that we found that as the radius decreases, the charge density increases, this explains why a typical discharge rod or wand would end up having such a small ball on here, because we want it to discharge here. This has a real-world application. I just want to remind everyone that Ben Franklin was one of the founders of our country, but also electrostatics. And his idea was that our lightning rods, which we want to prevent lightning strikes, should be shaped this way and not this way. Well, England was not happy with Franklin, and they went with the dome as opposed to a very, very, very pointy radius. Why is the pointy radius so important? Well, look, the charge density is so great at that point. The electrons are going to end up having a density so great, they're going to start throwing each other off. And this has ramifications of, if you don't want a lightning strike, use lightning rods. Lightning rods are supposed to prevent lightning. And if you give me a moment, I'll put this on here. Well, that didn't take very long. I just put the lightning rod at the top of the Van de Graaff generator. I'll now turn it on, and we'll see that we're not going to get any discharge at all. Up here you can see the point, and we have no discharge whatsoever. All the electrons are going to that point and jumping off. Pretty awesome. A real-world application of this little lightning rod can be seen next time you're flying. Look at the wing. Look out the window and you'll see on the wing, you've got this massive metal tube much like a hollow metal ball going through the air. It builds up charges. What you want to do is put little lightning rods on the back of the wings. Next time you're flying, take a look at the wings. You'll see little tiny, they almost look like nails or points that come off the backside. As you build up static charge, they simply leak back off. So lightning rods prevent airplanes and anything else from getting struck by lightning. That's your quiz for today. Thank you for watching another Idealized Science Institute video. We are a nonprofit organization. If you like what you've seen, be sure to like and subscribe. And if you want, leave a comment below. It's helpful to us. If you can financially support us, go to our website and hit the donate button. If you can't, simply by sharing these videos with other teachers and students in your life will be helpful. While at our website, you'll find that we have our Idealized Science Institute book that'll help you engage your students in dialogic discourse. There you'll also find we have a podcast where we break down educational research. We also have long-form lessons. If you're a teacher, you can watch these and go in the very next day and enact these. Along with this, we also have many other resources, including more quick quizzes. So thank you for watching, and we hope to see you in the next one.